to practice next is going back and forth between polar coordinates and rectangular coordinates. If I'm given an ordered pair in one coordinate system, I should be able to translate and talk about it in the other. Now, what I attempted to do here, because there wasn't a nice way for me to, I couldn't find one anywhere else, is I tried to draw circles and match them up with the grid. So here's radius 1 and 2 and 3 and 4 and 5. What we find out is here in SMART, they're not terribly, they're not anywhere near perfect. So here my R equals 1, I missed a little bit here in 2 and 3 and 4, but I'm spot on here and here. So they're going to get us close, but again, not going to be perfect. So let's say that we have, maybe in blue, maybe I am at 2 and pi over 4 in polar coordinates. And I want to figure out where 2, of course, is my directed distance. And I want to figure out my x and y coordinates for that. Notice what I'm doing here where I'm making a little right triangle underneath it, and going from polar coordinates into rectangular is actually very much what we did when we were breaking our vectors into component form. If I want a piece in the x direction and I want a piece in the y direction, I know my hypotenuse, I know my angle, I can use my sines and cosines. So I was going to do this on a different slide, but maybe I can sneak it up over here and make room, where x is going to be r times cosine theta. Let me get rid of that. Okay, sorry about that. My y-coordinate, my component in the y direction is r times sine theta. So if I'm looking at my polar coordinate, 2, straight line 2 from the pole, and pi over 4 for my angle with the polar axis, x is 2 times cosine pi over 4, which is 2 times the square root of 2 over 2, which is just square root of 2. So not quite 1.5, but close. My y-coordinate here is going to be boring because I'm at a 45-degree angle, but 2 times sine pi over 4 is also 2 times square root of 2 over 2, and also equal to square root of 2. So in rectangular coordinates, if I were on my rectangular grid, I would call this point square root of 2 comma square root of 2. And if we look, it looks like that's pretty close, about 1.5 comma about 1.5. This is my xy in rectangular, and here's my r and theta. So maybe I'm going to pause the video and I'm going to put 2 or 3 more points on here, and then I'm going to turn it back on, and then you'll see those points, and then you guys can pause and convert them from there. Okay. So let's look at the point 3 comma 2 pi over 3 and 5 comma 7 pi over 6, and go ahead and pause the video again and then find those coordinating rectangular coordinates, I guess, corresponding rectangular coordinates. Okay, so 3 times cosine 2 pi over 3 and 3 times sine 2 pi over 3. Make sure you get your signs, your plus and minus signs. Correct, there is a negative sign hanging here, but it's kind of lost in my equal sign. We can always do a quick double check. If I'm in the second quadrant, I know my x-coordinate needs to be negative and my y should be positive. In the third quadrant, both are negative. In the next set of examples, we will be starting with rectangular and going back to polar. Okay, so here are some polar coordinates, and now we want to go to rectangular from that. What we're not going to do is use the same conversion factors that we just finished. X equals r cosine theta, or y equals r sine theta. Those are both fine, but they're really only for going from polar into rectangular. If I want to go rectangular into polar, I know I need two things. There's two measurements that I need. One of them is we need to find that directed distance, or that straight line distance, r, from the pole out to that point. And then we need to find our angle theta that we make with the x-axis to the polar axis. Now, when we know the x-coordinates and the y-coordinates, now what we're looking at is Pythagorean theorem. We say, well, I know that x squared plus y squared would be equal to r squared. So in our case, we would say 2 squared plus 2 square root of 3 squared equals r squared. 4 plus 4 times 3 is 12. R squared is 16. So r is going to be 4. We of course could write it in terms of -4 if we wanted to, but let's stick with a +4, and then we just need to find this theta. If we have our x coordinates and y coordinates, we've done this before as well, we know that tangent of theta is equal to y over x. So tangent theta for us is 2 square root of 3 divided by 2, or just plain old square root of 3. In the first quadrant, the tangent is square root of 3 at pi over 3. The corresponding polar coordinates for this point here then are 4 and pi over 3. Alright, so our two conversions here, maybe I shouldn't have put them in blue, but I did. And we can find our r with Pythagorean theorem. We can find our theta using the arctangent, the fact that tangent is y over x. Go ahead and pause the video and do the other two for me, please. Okay, here we go. Also notice I slid my purple dot over where it belongs. I started out planning one thing and then I changed where I wanted it. I forgot to move my purple dot. So he's really supposed to be over here. Our r for this top left guy here, our r is the square root of 50, so 5 square root of 2. 3 pi over 4 is the angle that I put down here, but do understand that there are other names that we could give this. Okay, if I wanted to count in the negative direction, then this would be negative pi, which this would be negative 5 pi over 4, if we wanted to say that. Okay, or we could talk in terms of this angle here with 7 pi over 4 and call it negative 5 square root of 2 going in the backwards direction. Okay, these aren't unique, but I do need to make sure that I give a second quadrant angle there and not pick one of the others. Same thing over here with my purple dot that I slid over. The radius, the radius is 8. And if we count 3, 4, 5, 6, 7, 8, that was concerning to me that it was between 5 and 6, and now it looks closer to 8. We could say 11 pi over 6. Or we could say 8 if I said I just want to talk about going backwards. Pi over 6, we did talk about that. Okay, we could add or subtract 2 pi to any of these. We could even add or subtract pi and then make the 8 negative. So again, the blue ordered pairs are not unique, okay, to this point here, but the purple ones are. There's only one purple point for every address. One address for every rectangular point. So hopefully this helps with your conversions. Your book does a little bit with functions, but please read example 5 and a little bit above it. I think that should point you in the right direction.